Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing with our examination of free radical reactions, specifically monohalogenation free radical reactions. We left the last scribblecast lecture with a question, and that was why, when you treat propane identically with two different halogens, that is Cl2 and Br2, do you get such different behavior in the chemical reactions? That is, why is chlorination so non-selective? That is, the secondary chloride, which would go via the most stable radical, does not hugely predominate. While in bromination, it's very selective, and the secondary radical, which produces the isopropyl bromide, actually is in 98% yield. Any difference in this observation, any differences in the reaction mechanisms must be the reason for these differences observed in the product distribution. So let's begin by taking chlorination, and remember we're going to be examining the first step in the propagation step, which is hydrogen abstraction, because it is the rate determining step. Now, if I am going to look at hydrogen abstraction in chlorination, so let's start with chlorination. We're interested in monochlorination. Okay. And we're going to react propane with Cl dot. We're going to examine what actually happens at the secondary carbon. So I'm going to have Cl dot. And I'm going to be reacting this with H. And off of here I've got a C. I'll have an H. A CH3 and a CH3. Now what's interesting in the case of chlorination is that the chlorination hydrogen abstraction step is very exothermic. It's an exothermic reaction. And the highest energy state is achieved early in the progress of the reaction path. What does that mean? Well, I'll try to represent this in the transition state. The chlorine is hardly started interacting with the hydrogen, and the hydrogen has only slightly begun to leave the carbon. So we have bond forming. Here. We have bond breaking. Here. And I can finish this. The double dagger. Now it's very important to show what's happening with the lone electron, and we can symbolize this using partial dots. Now I'm going to exaggerate I've made this delta dot much larger because the hydrogen's only started to leave and hasn't completely left. And so this is my transition state. And the delta dot on the carbon is much smaller. And so this would go on to give me my radical. And I'm interested in the transition state. Now let's look at the potential energy diagram for this step. So here's potential energy. And this step is exothermic. So here's progress of reaction. I'll just put time here. And we'll start here. And what we have here is a chlorine dot and my CH3, CH2, CH3. And we progress through a transition state. Now we're going to have two different lines here. We're going to have, and I'll make one blue. The blue line will be to HCl and the isopropyl radical. Okay, so CH3 bracket twice CH dot. And I'll use another line which will be to HCl plus CH3, CH2, CH2 dot. And remember, primary radicals are less stable than secondary radicals, so I drew it at higher energy. Notice the difference in the energy of activation blue energy of activation here and the black energy of activation. There's only a slight difference between the energy of activation for the primary radical, so let's call it primary, and the E-act, the energy activation for the secondary. And that one of the reasons there's very little difference in energy between the two is because the reaction is heavily exothermic. Another interesting point is if this is the starting point of the reaction and this is the end point, halfway is approximately here. And the interesting thing to note is that this would represent the halfway point in the hydrogen abstraction, and that the transition state does not occur at the halfway point. And I'm a little bit off. It's probably more like here. Now, we're used to thinking about transition states as halfway points in reactions, but in actual fact, the transition state is better described as the highest energy structural form that is traversed in the transition of reagents into products. And so it occurs at the peak. What this means is that the transition state, because this step is exothermic, is forming early in the reaction. And a consequence of that is there's very little difference in the energy of activation. Now, because there's no difference in the energy of activation, a lot of molecules make it over both hills, which means you're going to get, you're going to get your 55% one product and 45% the other, with little selectivity. Another way of looking at this is to go back to the structure of the transition state. Because the delta dot on carbon is so small, because the hydrogen has not left, there's very little radical character on carbon. Hence, the difference in stabilities of the radical has very little to do with the transition state. Stability difference of radicals, since it has little to do with this transition state, does not affect the outcome of the reaction. This is seen in this potential energy diagram as very little difference in the energy of activations. So chlorination is non-selective because the rate determining step, hydrogen abstraction, the rate determining step of hydrogen abstraction is exothermic, very exothermic, causing the energy of activations to appear early in the reaction, the transition state to resemble reagents in which there's little radical character on carbon, and the resultant little difference in energy of activation leads to a lack of selectivity. Well, that's the case for chlorination. What happens if we switch things around and try to look at the case for bromination? Well, in bromination's case, we're going to do the same thing. We're going to work with Br dot, and this time we're going to have Br. We're going to have the hydrogen almost completely removed. And we're going to switch the nature of our delta dots. I'm going to put a very large delta dot on carbon and a very tiny one on bromine. So I'm going to suggest that this transition state that's occurring, the H is almost completely off, so this transition state is resulting late in the reaction and resembles the products more than the reactants. And so let's see if we can change things. We'll do the same colors. And see what we get. Okay, so what we're going to do now is we're going to start with blue for the isopropyl hydrogen. We're going to start reaction here. This is time 0. And we're going to go like that. And now we're going to do the primary. And I will do that. See if I can round it out a little bit. There we go. Okay, and remember my drawings are a bit crude. It is a scribble cast after all. And so in this case I've got Br dot plus propane and the black is my primary radical, so I'll draw this up here beside it. And I've got HBr forming this time, plus CH3, CH2, CH2 dot. And for the secondary radical, I use blue, so that's HBr plus, plus bracket CH3 bracket twice CH dot. Let's rub that out. Okay, and so we're looking at the hydrogen abstraction step. I'll leave the chlorination numbers down there. And then this time we're getting 98% of the secondary forming. Only 2% of the primary. And we can draw in our energy of activations. So here's the energy of activation, okay, for the secondary. And Here is the energy activation for the primary. And you'll notice something different if you look at the potential energy diagram. The first thing you notice is that this step is endothermic for bromine. The endothermicity results in much larger energy of activations than we saw in the primary and secondary cases for chlorination. Not only that, but the peaks of these energy of activations occur well beyond the halfway point of the reaction. If I was to start here and mark the end here, halfway between would be somewhere here. And so this transition state, or the high energy structural forms, are achieved later in the reaction. That was when the Br dot has almost completely pulled off the hydrogen. The consequence of that is the carbon now bears a lot of radical character, a huge amount of radical character. And because of that, the large amount of radical character means radical stability becomes important. This is reflected in the differences of the energy of activations. The large difference in energy of activations means more molecules make it to the secondary radical than the primary. In fact, 98%. Net result is you get a 98% or very selective product distribution. This is all caused because the reaction's endothermic. Being endothermic leads to large difference in energy of activations caused by the transition states being achieved late in the reaction and resembling the radical more on carbon than on bromine. And therefore, carbon radical stability becomes important. So there you have it. And by the way, I should change the name, I guess. I've got the title sitting chlorination. It should be, for this one, bromination. Okay, so there you have it. Bromination is highly selective, chlorination is not. Let's review one more time. The case of chlorination, the hydrogen abstraction step was exothermic. This led to transition states that had very little differences in energy of activations and formed early in the reaction. Because they formed early in the reaction, the H was not pulled off very far and there was very little delta dot, very little radical character on carbon. So the stability of carbon had little to do with it. And we saw that in the fact that the energy of activations were almost the same. Then we came to bromine. Bromine was different. The reaction was endothermic. The endothermicity led to transition states that formed late in the reaction. They resembled more radicals having larger delta dot. That radical stability became important on carbon, and it was seen as larger differences in energy of activation that translated into a very selective reaction. Okay. Now, the relative rates of the different selectivities of the halogens can be determined. And when comparing the kinds of hydrogens, you can contrast the relative rates. For example, if we look at chlorination, Cl2, and we compare primary to secondary to tertiary, we find chlorination not to be hugely selective. That is, we set primary to 1. We find secondary hydrogen abstractions are 4.3 times faster, and tertiaries are 6.0 times faster. Now these numbers will vary slightly depending on the reaction conditions, but they're a good rule of thumb. Bromination, on the other hand, appears to be much more selective. If we set the primary to 1, secondaries are 220 times more likely to undergo hydrogen abstraction. And if you compare tertiary to the primary, it's 19,400 times faster. Now this can all be translated using these numbers to actually calculate a percentage composition in a monochlorination reaction of any alkane. For example, let's try the chlorination of propane, the one we've just looked at. If I consider propane, I see I can get 2 monochlorinated products, and only 2. If I react propane, I can get the isopropyl chloride. We've already established this. Or I can get propyl chloride. And label these two structures A and B. Now, structure A can be formed, if I look at structure A and draw it here, this can be formed if the chlorine radical abstracts a hydrogen from a primary position. In terms of statistical probability of molecular collision, there are 6 chances of colliding with a suitable hydrogen. See, any of these CH3 hydrogens will give you this product. And so, statistically, this has a 6 to 2 chance of forming this guy, whereas in B, there are only 2 hydrogens that can be pulled off that will allow you to replace with a chlorine. And either of the 2 middle hydrogens will give you isopropyl chloride. That means while the relative rate of A may be 1, there are 6 chances that you're going to produce that 1. And that gives you a value of 6, 1 times 6. In chlorination, there's factor 4.3 times faster, but there's only 2 hydrogens that could be pulled off. So statistically, we get 8.6. If we add this up, we get a total of 14.6. If I want the percent composition of A to B, A's percentage will equal 6 over 14.6 times 100%. If I solve that, I get equal to 58.9%. If I do B, B equals 8.6. Whoops. I'm mixing up my numbers here. Sorry. 41.09%. 8.6 over 14.6 times 100%. And that will equal, now it's my 58.90%. Okay, now you notice this is very close to the 55-45 that we actually got experimentally. The variation is probably due to the variation in the relative rate numbers. What about bromination? What if we replace this now and we do the same thing for the bromination? So we have bromines here. Well, we have to use the bromine numbers for relative rates. The statistical probability is the same. So for the first one, it's 1 times 6. But this number becomes 220 times 2, which is 440. Which means when I add this up, I get 446. Wow, that's a huge difference. 6 here divided by 446 times 100% is going to be a very tiny number. In fact, it is. It's 1.35%, almost 2%. And if I take 440 divided by 446 times 100%, I get 98.65%. And so using this type of approach, we can determine the actual percent compositions. Now, in your notes, you're asked to do this for the molecule isopentane. And I just want to show you one of the complications in this. The question read, predict the mole percent composition of the isomeric products from free radical monochlorination of isopentane. And then you have to do it for bromination. Isopentane is this molecule. And the only tricky part about this is finding all of the monochlorination products. So I'm going to give you a hand with this for this one. And there are other questions in your notes you can try this for. And so you've got to be able to draw all the monochlorination products. Now here's the question. Well, I see clearly there's a CH3 and I could monochlorinate the primary position. So this certainly would be one monochlorinated product right here. And if I use the numbers I had gotten before, because it's primary, 1, I can multiply this by a number of the probability of forming it. Now that depends on how many other chlorinated products I get. So let's draw them all first. The next is a CH2, a secondary, so I can substitute there 1 hydrogen for chlorine. And this would be a different chlorinated species. And I don't think there's any problems with that. And then there's the tertiary position. If I replace the hydrogen in tertiary position, I get this guy. Is that it? Well, you say yes. I've done the primary carbon, I've done the secondary, and I've done the tertiary. Be careful. Some primaries are different than others. For example, this primary position here has next door to it a CH2. But the primary positions here and here have next door to it a CH. So if you put a chlorine here, you've got, yes, a primary position chlorinated, but you've got a different molecule. Try naming this, okay? This guy is 1-chloro-3-methyl-butane. 1-chloro, okay, so let's write that down. 1-chloro-3-methyl-butane. The bottom one, however, is 1-chloro-2-methylbutane. Are those the same molecules? They have different names. Because they have different names, they're different molecules. Okay, what if I put the chlorine up here? What if I went CH2Cl and made this guy CH3? Is that different? Well, name it. 1, 2, 3, 4. It's 1-chloro-2-methyl again. It's the same. So there are 4 monochlorinated products. Now, once you've got them, you can figure out the probabilities. This is primary, so it gets 1. There are only 3 hydrogens that can be pulled off that would give you the same product. So it's 1 times 3. This one is off the CH2. There are 2 hydrogens there. It's secondary. Secondary uses 4.3. The tertiary, there's only 1 hydrogen. Its relative rate is 6, so 6 times 1. And lastly, another primary, the 1-chloro-2-methylbutane, but any of these methyls could give it, so there's 3 there, 3 there, that's 6 hydrogens. 1 times 6. All right, so I've gotten you started with the chlorination product, and you should be able to figure out your percent composition from here. What we want to do now is consider this monochlorination for those special alkanes, the benzylic and allylic cases. And what we're going to do now is consider the selective and non-selective chlorination and selective bromination, and what would happen if we tried a benzylic molecule like ethyl benzene. Now with ethyl benzene, you could have, in the case of both chlorination and bromination, two products. Now, I'm going to tell you right now, radical substitution on the hydrogens of the ring is not as fast as substitutions on the alkane. So we're going to focus on those positions. So we can get CH3 Cl plus another aromatic ring, CH2 Cl. Likewise for bromine, we could get CHBr, CH3 plus CH2 Br. All right. Now, remembering that chlorination is not selective, one might beg to ask the question, okay, there's not much radical character, granted, but this is a primary radical, and this is benzylic, and benzylic radicals are resonance stabilized. So benzylic radicals are the most stable. Does this reaction still remain non-selective? And the answer is, because there's very little radical character in the transition state, the stability of the benzylic versus the primary has little to do. In fact, the percentages are almost exactly the same as what you got for propane, 56% and 44%. But when we came down to bromination, remember, the secondary over the primary was 98:2. And secondary is a little more stable than primary. What happens when you use benzylic compared to primary? The most stable possible. Well, bromination, being endothermic, formed late in the reaction, had lots of radical character, so stability of radicals became important. Benzylic radical, most stable, is 100%. And none of the other forms. Okay. Likewise, allylic systems could lead to the same thing, but allylic systems have one complication. Suppose I use cyclohexene. Cyclohexene has two allylic positions, here and here. There are hydrogens there that could be abstracted. And if I hit my cyclohexene with Br2 and H-nu, I could envisage a very selective reaction substituting in the allylic position. Now notice, if I had done chlorination, I would get percentages of substitution here. And by the way, substitution here or here are symmetrical, so they're the same thing. But with bromination, the allylic's most stable. But I have a problem. Well, what's that problem? We studied Br2 reactions on alkenes last semester. And Br2 additions to alkenes gave trans addition of Br2. In other words, this is electrophilic addition. Electrophilic addition is not a radical reaction. And we studied this mechanism. This is free radical halogenation. It's a completely different reaction mechanism. Free radical bromination. Or halogenation is fine. Okay, so, oops, that shouldn't be 2, that should be just BR. Okay, now, the problem is we have two reaction mechanisms competing with each other. Suppose we want free radical bromination. We want to brominate the allylic position. We don't want to add bromine across the double bond. Think about the difference in the reaction mechanisms. In the top one, electrophilic addition, Br2 made an approach and collided with the alkene. This broke that bond, making a bromonium ion. And then the Br minus came around and attacked the back side. And you got trans addition of Br. So in order to do electrophilic addition, we have to get a collision with Br2. But in free radical bromination, the first step is the initiation step. Br2 does not collide with the alkene, it falls apart. To what? It becomes 2 Br dots. So the real big difference between these two mechanisms is that in the first one, the Br2 must collide with the alkene. In the second one, the Br2 must not collide with alkene. It must fall apart to Br dot. If it falls apart to Br dot, then you'll do the free radical bromination. So we want to slow down Br2 collision with the alkene. Give it time to break up. How can we do that? Well, we can favor free radical bromination by 1, using dilute solutions. Give the solution time, or the bromine time, to form radicals. Dilute solution of Br2. Okay. So very dilute solution of Br2 or low concentration of halogen. The next thing we can do is high temperatures. Higher temperatures favor radical formation. Just remember, we use Br2 in light here. Well, you can use Br2 in light. You can use higher temperatures. High temperature helps the bromine to form radical. These two conditions will help favor free radical bromination, but they will not totally eliminate the electrophilic addition side reaction, and so you're going to have impurities. If dilute solution or low concentration of halogen is so important, it would be really ideal if we could find some way of having only a trace amount of Br2 present, and that it would react, and then more Br2 would form. And there is a way of doing this. How can we do this? Well, with a reagent that is basically derived from this molecule. This molecule is butane dioic acid, 1,4, but you don't need to say the 1,4. 1,4 butane dioic acid, or just butane dioic. Butane dioic acid has a common name. It's called succinic acid. Now, if you heat succinic acid, the two ends will collide. It can wrap around and react with itself and kick out a water molecule. And if you heat it, you can produce this anhydride molecule called succinic anhydride. Succinic anhydride. If you treat succinic anhydride with ammonia, you can replace the bridging oxygen with the bridging amine. If you do this, you now have an H here, and you get succinimide. Now, there are reagents which allow you to replace the hydrogen on the end with a bromine. We've seen these types of reagents in alcohol chemistry. Reagents like PBr3. Brominating reagents that will replace OH groups with Br that will work on NH groups. You can use PBr3, SOBr2, and you can make a molecule like this. And this molecule is our magic reagent. It's called N-bromosuccinimide. That's a long word, so often over an arrow in a reaction, you'll just see the term NBS for N-bromosuccinimide. Now, what's special about N-bromosuccinimide? If we use N-bromosuccinimide as a reagent, if we use NBS, either on, for example, our allylic cyclohexene, or even our benzylic, like our ethyl benzene we had earlier, and you react this, say, with NBS. The solvent's often a solvent like carbon tetrachloride. And you use HNu. Same thing here. NBS, carbon tetrachloride, HNu. Well, as expected in the benzylic case, you get bromine. Notice electrophilic addition's not a problem on an aromatic ring. You can't get that. It's again selective. There's no surprises here. You get, for the allylic, you get only, oops, put the double bond in the right space, only the free radical reaction. Really quite nice. Why? How does N-bromosuccinimide do what is so difficult in the Br2 case? And the answer is N-bromosuccinimide delivers a low but constant supply of Br2. How does it do that? Well, to answer that, we have to look at the propagation steps in the allylic reaction. And let's start with that. Remember, in the propagation, the first thing is the hydrogen is abstracted by a halogen radical. In this case, we've got bromine dot. So the first step, of course, and I'll explain where the bromine dot comes from. Bromine dot, when we have HNu, we're in a solvent. This is carbon tetrachloride. Don't get confused by it. It's just solvent. Carbon tetrachloride is just solvent. And in this case, we've got Br dot abstracts, becomes HBr, and we get our allylic radical. Okay, no surprise there. This is just standard the standard thing. What's interesting is the HBr does not just sit around now because there's lots of N-bromosuccinimide around. And it turns out N-bromosuccinimide is very sensitive to the presence of acid. The acid, or HBr, reacts. Okay, and remember there's light. There's still light here. H nu carbon tetrachloride. That's still, the whole system's being bombarded with radiation. That gives us Br2 and succinimide. And now, you remember your next step is the radical. The organic radical reacts with Br2. Okay, and we have our H nu and light. Remember the H nu CCl4, the light really was just to get the reaction going. And you get your allylic bromide, and you get a new Br dot. Now let's just link it up. The HBr came from here and reacted. The Br2 came from here, goes there, and the Br dot goes back to the beginning. So what's happened is the top and bottom really are normal propagation steps. N-bromosuccinimide has just inserted itself in the middle. And notice you never have Br2 around. This guy's never around. Not until a Br dot has produced HBr, and HBr has pulled a Br off to make the Br2. And that won't happen until the Br dot reacts to make HBr again. So there's never a big concentration of Br. There's no Br2. You take the alkene, you add N-bromosuccinimide, there's no Br2. Now where does the first Br dot comes from? Well, that's where the light comes in. Trace amounts of water can produce Br dot, but the H nu will photolyze this N-bromosuccinimide, and you'll get Br dot. There's always a trace. In fact, even with the reagent, there's always a tiny amount of bromine impurity, which will photolytically get active. So there's a tiny amount of Br dot. It reacts. The HBr starts reacting with N-bromosuccinimide, makes a Br2. The Br2 reacts with the allylic radical, Br dot. There's never any large amount of Br2 to risk electrophilic addition, that the Br2 will maybe electrophilically attack. Okay. Well, so N-bromosuccinimide is a nice reagent, and you should be aware of it and be able to use it. Okay, well, there you have it. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.